methods that we can use when we have high-dimensional data and we want to represent them so that their mutual relationships are captured in a low-dimensional representation. Okay, so the idea is that we have lots of points, lots of objects, and we usually say, we use the M to say how many objects we have. The problem with these objects is that they are usually embedded in a very high dimensional space. So the typical object okay. We have many coordinates and we want to represent them in a low dimensional space. Because maybe we want to plot them. We want to plot our objects and we want that objects that are close, that are nearby to each other in their original representation in the n-dimensional space are also nearby in our representation, and vice versa. Of course, this is not always possible. For example, one possible way of reducing the number of dimensions when we represent something is just to remove some dimensions. We do what is usually called a projection. So, maybe you have two-dimensional data. If you want to reduce them in one dimension, you simply ignore the second dimension so that you represent each of your points with only their x coordinate. Okay, this is one perfectly reasonable way of reducing the number of dimensions. Of course, what I will say in the following part is important when it is useful when n is very high and we want to represent our objects in 2 or 3 dimensions. But anyway, just to have an idea, suppose that the high number of dimensions is 2 and we want to reduce them to 1. Okay, if we do like this, so we ignore one of the dimensions so that we represent the points like this. Do we actually preserve the distance relationships between every pair of objects? Yes and no, okay. Yes, because objects that are nearby in 2 dimensions still are close together when we come to 1 dimension. Why? Well, because they become even closer because we are removing the difference in the second dimension. But of course we can have 2 objects that are very far apart because they are very similar in the x coordinate but very different in the y coordinate. In this case, we are projecting them onto the x-axis into something that is not that does not represent them very well, because they look close even though they are very different. Okay. So this is one of the possible pitfalls. In this case, what's important maybe is to, well, carefully choose the coordinates to remove, for example. Or we will see later doing some coordinate transformation so that what's very important, the very important differences between the points are captured by one of the dimensions. But first of all, I would like to introduce an intuitive method to do this. So, suppose that we have an object. Suppose that we know the actual distance that two objects I and j have in the high-dimensional space. So let's call dij the distance between I and j in the high-dimensional space. And suppose that we want to represent this object in a low-dimensional space that we can call, well, let small n be 2 or 3, the dimension of the space where we want to represent our objects. So, our objective is represent our m objects so in 2 or 3 dimensions. So for every object m, we want to find a set of coordinates xi in Rn, small n, such that their distances, their actual distances are, well, they cannot be precisely preserved, but we can at least assume that they are well represented. Where represented is something that we need to define. Okay, is the problem clear? So, our input data of the problem are these mutual distances. Well, it's clear that this this problem cannot be solved exactly. For example, suppose that you have 3 objects and that the mutual distance between object I and j is, of course, 0 if I is equal to j. Every object has distance 0 from itself. And 1 in all other cases. Where E and J, of course, are okay, from 1 to 3. Can we place these points in a 2-dimensional space? Yes, there will be just the three vertices of an equilateral triangle. So, if we place the 3 points so that they are at the vertices of an equilateral triangle where all sides are 1, we are done. What if we increase the number of points to 4? We want to represent 4 points so that their mutual distance is always 1. Well, actually we can do it in 3 dimensions. We just put them at the vertices of, how can I represent it? Maybe this way. So look at it in 3 dimensions. It's a triangular pyramid, a tetrahedron. Okay. All sides are at length 1. The problem is that no matter how you try to flatten this to 2 dimensions, you will never get all mutual distances to equal to 1. It's impossible. So we can expect that if these distances are computed in a high-dimensional space, there's no way to reproduce them exactly in 2 or 3 dimensions. Well, actually there's more to it. Oh, no. So, okay, suppose that we know, okay, we know what distance, what mutual distances we want to reach. We're not sure that we can do it exactly. Now, suppose that, okay, in a 2-dimensional space, I decide to put object I here and object J here. Okay, so actually we have a coordinate system where this is xi and this is xj. So we represent the points with the vector of their coordinates. Okay. How do I compute their distance? Their distance in 2 dimensions. Well, the distance is simply the distance from I to J. No. Keep in mind that this dij is constant. Okay, this is what we want to obtain at the end. It is the ideal distance that we want to give to our points. The real distance between our points in 2 dimensions is the difference, let's say, xj minus xi, the Euclidean norm of the difference. Okay, we want this distance to be somehow close to the real distance, dij. What I want to create now is an iterative procedure so that if 2 points are too far apart, okay, let's move them close together. If they are too close to each other, let's move them a bit far apart. This is somehow what we expect to happen if we assume that, you see, if the 2 points are too far apart, then we would like to move them together, to move them towards each other. This is precisely what in the physical world is done by a spring. The idea is that, suppose that these 2 points are connected by a linear spring which has, you see, when you don't apply any force to the spring will have its own natural length, its own rest length. So, suppose that we connect the 2 points I and J with a spring that has a natural length equal to dij. The idea is that if the 2 points are too far apart, the spring will tend to move them close together because it will apply a force directed towards each other point. If the 2 points are too close together, the spring is compressed and it will push the 2 points in opposite directions. Of course, we don't only have 2 points, we have lots of points. And so the idea is that we connect every pair of points with the spring whose natural length is the one that we want to achieve. Okay. Let's be a little bit more quantitative. How does actually a spring work? So, if you have the 2 points I and J with their coordinates and you connect them with the spring, the force that each point feels because of the spring, the force that is exerted by the spring to the point, is proportional to the spring's elongation or compression. So let's call Fij that for the force that point I receives from the spring connected to point J. So the opposite will be Fji. Of course, this force will be represented by a vector. But let's see the law that determines the modulo of the force, the intensity of the force. Well, the intensity of the force is regulated by the so-called Hooke's law. Which states that the intensity of the force is proportional, and let's call K the proportionality constant, to the difference between the actual difference, the actual length of the spring, which is xi minus xj modulo, and its own rest length. So, if the distance between the endpoints of the spring is exactly the one that the spring would like to achieve, then this is 0, and the 2 points will not receive any push or pull. They will remain there. On the other hand, the larger the difference between these two values, the stronger the pull or the push of the spring. Okay, so this is a fundamental law of physics. Of course, it's an ideal law, valid only for very ideal springs and so on. Now, this is the modulo of the force. Okay. What about the direction of the force? The direction of the force is precisely the direction of the difference between xi and xj. So the force exerted by the spring on the point xi will always be either towards xj or away from xj, but always in this direction. The spring is unable to exert any force in a perpendicular direction, of course. So, how do we set the direction of a vector? We take the modulo 1 director, I don't know the English name, the unit vector. Thank you. That direction, which is of course, so the force vector from node I to node j, the force vector of, exerted on node I by the spring that connects it to node j is, so it's k times so j its modulo times the unit vector from node I to node j, which is xj minus xi divided by their distance. Of course, I might have misplaced a sign. Okay, so if this is xj and this is so xi and this is xj, then this part represents the unit vector going from xy towards xj. Okay. Now the force should be in this direction when xi and xj are farther apart with respect to the rest distance. So this must be positive when the distance, the actual distance between the 2 points is larger than the ideal distance, which is precisely the case. So these two are in the correct order. There was a 50-50 possibility, but I think that the signs are correct like this. Okay, so this is the force from node I to node j. Now, what is, we have many points, okay? Lots of points, and they are all suppose that they are all connected with springs. how do we determine the force that is exerted by all springs on each point? We add up all forces that are exerted on the same point. So, it is that the total force exerted on node I is simply the sum for all nodes j different from node I of the force exerted to the spring on node I connected to node j. So this is node I, and it's connected by springs to the remaining nodes. It will fill many pools, or maybe one of the springs is too short so that the point is projected in the other direction. But anyway, the overall force is the sum of these vectors. You can also observe here that, as we might expect, Fij is exactly the opposite of Fji. This scalar part remains the same. This vector is reversed. Okay, but now that we have these forces, how do we proceed? So the idea is that, well, let's just simulate this as if it was a physical system. So we assume that every point has its position, and the final position is what we want to find for every point, and also a velocity, speed. Why do I want a speed? Because, as you know, Newton's laws, the force is related to acceleration. In general, the acceleration of a point is proportional to the force, the total force exerted on that point. So, let's say that every point has a position xi and a velocity vi. Of course, with a fundamental link between them, the velocity of the point is the derivative of its position. So it's actually the amount by which the position changes in time. On the other hand, the amount by which the velocity changes in time is proportional, let's call alpha the proportionality constant, to the force, applied to node I. So, if we wanted to solve exactly, analytically, this problem, we would have all the necessary data. We have this set of differential equations. ordinary differential equations. We set some starting points, for example, random positions and zero velocities, and we see how the system evolves. However, we want to solve this experimentally at the computer. So what we do is actually discretize these equations. And let's see how we do it. Okay, I hope that you wrote down this equation because I'm going to erase it because unfortunately I put it exactly in the center of the blackboard and I will need the center of the blackboard. So, we want to make this, our points to move according to these equations, assuming that these equations will move the points so that the springs will be as close to their rest position as possible. So the idea is that okay, we simply start with a random position for every point. Of course, a random position in R small n, which is our target space. And we also account for the speed of each element. Let's say it's 0 initially. So let's start with our points in random positions, all connected to each other by a spring, and each spring will pull them or push them, making them change their velocity. So we want to actually repeat the following procedure. First, the velocity of each particle will change proportionally to the force exerted to that particle, to that object, to that point. So we actually compute of course for all i's, we compute the force exerted to node I given their position, their neutral positions. Of course, this as we saw, these forces are computed considering the Hooke's law. But now, again, for all particles, we update their velocities. This is the real equation that connects the velocity to the force. But actually, we can discretize it by applying this with a constant force for a small amount of time, so that it becomes its discrete version. So we can compute a variation of velocity that is proportional to the force and to a parameter, a time step, which we introduce in the algorithm. Of course, we want this to be small. The smaller is this delta t factor, the more accurate is this approximation of the true continuous equation. So we can compute this variation of velocity. So, in the end, this is the variation, so we add it to the current velocity. So, at every step, we update the velocity of the point. And now we do the same with the position of the point. By this continuous equation, we get this discrete approximation where we assume that in the time delta t the velocity is constant. So this is the variation of position is velocity times the time, of course. And so we can also update this. Okay. Is this clear, more or less? Do you have any questions about this? So, this is actually a machine simulation of a physical system where you have m points with mass alpha connected by springs, each having its own rest length, and with a given elasticity constant k that we saw in the Hooke's formula, and we let it evolve. Okay, what will this system actually do if you let it evolve? Consider the case of 2 points connected by a spring. Suppose that you place them too far apart. The spring will pull them together. But actually what happens here, because of the inertia given by the fact that the force acts on the acceleration, well, if you take 2 points connected by a spring, the spring is pulled, and you let them evolve, the system will oscillate indefinitely. Which is not what we actually want. We want the spring to pull the points up to its rest position. The problem here is that we are not in any way damping the speed. We want to add some viscosity to the system. So that, well, physically we want the energy of the system, the total amount of kinetic energy, not to grow, not to remain, well, actually it's not the total amount. Actually we want the total energy of the system to go down. The idea is that we need yes, to add some friction to the system. Either some friction or some viscosity. The idea is that at every time step, the velocity is reduced by a small factor. Eta is, as always, something between 0 and 1. And you see the effect of eta in the two extremal cases. If you put eta equal to 0, then at every step the velocity will always be 0. So you have a system with infinite viscosity. The particles are glued where they are and they cannot move. If you put eta equal to 1, you have no reduction of velocity, so the particles will keep moving and the system will likely oscillate. This is another factor that we have to consider. Okay, so this is a basic method where that actually solves this problem. The effect of this algorithm is actually to reduce as much as possible the so-called stress of the springs, meaning their potential energy. Let's say we can measure the stress of the spring between points I and J by this formula. I'm not going to derive it from the basic dynamic laws. This is not a physics course. But the idea is that the stress of a spring is 0 if the distance between its endpoints is precisely its rest length, and it grows like the square of its elongation or compression. And this algorithm actually minimizes, so this algorithm, the whole algorithm, of course, tries to minimize the overall stress of the system. So ideally, the minimum that you can achieve here is 0 if all springs have precisely their rest length, which is, of course, impossible in many practical cases. We can also generalize that algorithm. Here, you see, I have assumed that all pairs of points have a given distance, and that mainly it was this assumption that we can relax. I mean, this algorithm also works if some pairs of points don't have a preferential distance. It may be the case that some points simply don't compare to each other. So it doesn't matter if those 2 points are far apart or close together. For example, if you have Well, this may be the case, for example, with a friendship network such as Facebook. You have information about people who like each other because they are friends, because they like their messages, and so on. But not so you can have a measure of similarity between two people. For example, you count the number of times that one person likes the messages of another person. And the higher this number, the smaller the distance between these two nodes. But there are also nodes that you cannot compare in any way, simply because they have never looked at each other. So, if node I never expresses anything about the messages of node J, it doesn't mean that I and J don't like each other. It only means that I and J never had the chance of looking at each other's messages, for example. So some nodes are not comparable. So we can extend this algorithm by accepting that some of the Dij are actually, let's say, we add the special don't care value to the set of values that can go here. In general, Dij are all numbers, are all positive numbers. But we can assume that some pairs of nodes don't care about each other. And the idea to also consider these values is that, you see, some points are connected by a spring. So, let's say, not all possible points are connected by a spring. Okay, so for example, 1, 2, 3, and 4, we can have a situation like this. So 1 has a preferential distance from 2, 1 has a preferential distance from 3, but 1 and 4 don't care about each other. So there is no spring between them. How does the algorithm change about this? Well, the only point where it changes is when we compute the overall force exerted on node I. We simply modify, you remember it was the sum of all Fij. Well, of course, this sum should only be applied to nodes J connected to node I. Okay. Simply, there are some pairs of points where there is no force directed to each other. This way, we get rid of some of the springs. Now, if you look at this drawing, this actually means that, you see, node 4 only has a connection to node 3. Node 4 has no connection to node 1 and 2. D41 is the special don't care value. The problem with this is that this configuration is not really well defined. Suppose that this is the let's put some numbers, okay? Suppose that all rest lengths of the springs are 1. So, let's say the Dij matrix is, we have 4 points. Every point has distance 0 with itself. Then node 1 has ideal distance 1 from node 2. And from node 3, it has no ideal distance from node 4. Node 1 and 4 don't care about each other. Then node 2 had the ideal distance of 1 from node 3 and did not care about node 4. Finally, node 3 and node 4 had an ideal distance of 1. This is the connectivity matrix with that special value. Now, of course, the only way to precisely satisfy the mutual distances of points 1, 2, and 3, which are all equal to 1, is to put them in an equilateral triangle. So, in this case, these springs, the spring between 2 and 3 has 0 stress, and so S12 is 0 and S13 is 0. But now, look at what happens between nodes 3 and 4. The only requirement of node 4 is that it must be a distance to 1 from node 3. So node 4 might be here, with distance 1, but it might also be here at the same distance, or here at the same distance. Actually, it will fall here. Okay. We have no particular constraint on the actual position of node 4, only that it must be at distance 1 from node 3. Now, which of these position is best to represent our system? Well, actually, all these positions represent the system equally well because they all satisfy all distances. But if we want, you see, here we are falsely asserting that node 4 is close to nodes 1 and 2. Moreover, if we put node 4 here, our graph representation is more mangled. Okay, everything is put together even if it should not. The idea is that in order to have a visually better representation, node 4 should be put as far as possible from the nodes it doesn't care about. So we should assume that the don't care value asks the system to try to take those nodes out of the way. Among all positions of node 4, probably the best one is the one that puts 4 on the other side with respect to nodes 1 and 2. Simply because it has nothing to do with nodes 1 and 2. You see it from the matrix. How do we do that? Well, if we want to stay with our physical equivalent of springs and forces, we can add a repulsion between all pairs of nodes. we assume that all nodes tend to repel each other by a small amount. And the physical equivalent that we usually have is that of electrical forces. Suppose that all these points have the same, for example, positive charge, then they will repel each other by that's called Coulomb's law. So the idea is that we add, let's call it Fc, is the Coulomb's propulsion, between node I and node J. Okay, here the force is, okay, of course we have some proportionality constant, let's call it beta. It is inversely proportional to the square of the distance between the nodes. Okay, this is the modulo of the force. Now the direction, we need to set it on, well, let's take the usual unit vector. In this case, we want the force to be repulsive, so it will be xi minus xj divided by xi minus xj, like this. This gives the strength of the force, and this gives the direction of the force. So if you prefer, we can write it as beta times xi minus xj divided by the cube of the distance. Now, remember that we also have the Hooke's law. Let's call Fh the force by Hooke's law, so we can, which was k times something times the unit vector between the nodes. So how do we change this algorithm? Well, let's write explicitly how we determine the forces. So we need to repeat. Now, we start by setting Fi to 0. Then, for every j different from I, we add the Coulomb force exerted on node I from node J, and for every J connected to I by a spring, we also add the corresponding Hooke's force, like this. and we do this for all nodes I. Well, actually, first we determine the overall force for all nodes I, and then we compute velocities, and we update velocities, and we update positions. Okay. So just to recap everything. We started from information about the mutual distance of points. We formulate a physical equivalent where forces tend to pull things apart and push things together in order to minimize the stress of the system. And what we get is an algorithm that converges to some position that well, should minimize the stress. Actually, it minimizes the stress if we don't consider the Coulomb force. By adding the Coulomb force, of course, springs will always be more stressed than needed, but we have a system that treats better its objects. For example, another interesting example is this. Okay, suppose that we have 4 points, some of which have mutual distances equal to 1, while other pairs don't care values. So if we number points like this, we want the points 1 and 4 to have distance 1, but we don't care about the distance between 1 and 3. Well, with the Coulomb forces, where points slightly repel each other, we end up with a square. Without Coulomb forces, where these 2 points don't care about each other, we might as well end up with a situation where point 2 is here, point 4 is here, and points 1 and 3 are clashed together because they don't care about each other, they don't repel, they don't attract each other. So usually adding Coulomb forces tends to spread the graph better. What are the pros, the advantages of using this kind of algorithm? Well, it usually ends up with good configurations of points. Even looking at its evolution is nice because, well, it's actually mimicking a physical system, so you can see points that spread their position. Well, that's it. It has some disadvantages. The first disadvantage of this algorithm is that it has a high computational complexity. You see here, each step requires the computation of forces between all pairs of points. It means that it has every iteration has a big O of m squared complexity. Actually, every operation involves vectors of dimension n, but we are assuming that n is constant and very slow and very low, 2 or 3. So otherwise, we should have also n here. But, okay, n is just a small number. But the problem is that every iteration is big O of n squared. But how many iterations do we need to do? It depends. It mainly depends on what time increment we are applying to every iteration. If we want our system to be to simulate a real physical system, we want this delta t to be small. So we want very little progress at each step. If we increase delta t, we have larger steps at every time, but the system will not evolve like the physical one, and we should end up with some suboptimal solution. Tomorrow, maybe we will experiment with something like this. Okay. Another problem of this algorithm is that it's full of parameters. You see, you have, if you want to determine the forces, you need at least two parameters, k and beta. Then, which are the Hooke's constant and the product of the charges of the two particles, if you want the physical equivalent. Then you have this alpha, which is the mass of each particle. Then you have the time increment and the viscosity of the system. And you need to balance those parameters, I count 5 of them, in order to have a good behavior. So you don't want delta t too small, otherwise the system will evolve very slowly. You don't want eta to be too small because the system will oscillate, actually too large because the system will oscillate, but not even too small because otherwise you are breaking the system and it will converge with difficulty. Probably you want beta to be much smaller than k, because what's important to regulate the system is the Hooke's force given by the springs, while this repulsive force is only something that you add in order to spread the graph a little better. So this force should be smaller with respect to this one. Okay, anyway, maybe tomorrow we can try to play with these coefficients. Okay. You may notice that in this case, our starting point was mutual distances between points. So we never used the information that our points are embedded in an n-dimensional space. We didn't care about that. Actually, in this case, you see, this algorithm only requires to have ideal distances between points. We are not interested in what these points originally were. In fact, maybe you don't even have an n-dimensional representation for those points. For example, before I mentioned some social network where maybe it's easy to decide whether two people like each other, but you cannot decide it on the basis of their position in an n-dimensional space. Okay. So actually, the starting point is from here. So in this case, we have an algorithm that starts from what I called an external representation of our nodes and ends up with an approximate internal representation of the nodes. It starts from mutual distances and ends with coordinates in a vector space. Okay, there are, of course, there are many methods to do that. This is probably the most intuitive one, because we have experience with systems like this. Nothing prevents us from having a much larger value for n. This system will work for every dimension of the target space. It's simply mainly used with small dimensional spaces, but it's not necessary. Okay. Are there any questions?
The force between data repulsive. Why we don't add it only to points who don't care about each other, and add also to the points who have the spring between them?
I agree, that's another possibility. So you do this step only for where J is not connected to I. Yes. It's yes. So you take care of the fact that the spring size should be actually exactly 1. Yes. It's for some reason the elementary descriptions always don't consider this fact, but in fact it's best. So that actually you only need one loop where you see if the two nodes are connected, then yes. The other actually there is one problem, but I'm not sure it's a problem. You don't have a physical representation of the system anymore. It's difficult to devise a physical system where these two repel, but this and this don't. Okay, so if you put charges on the points, they will either repel or attract each other. So your suggestion is fine, it will surely work, it's no more physical. Let's say that, it's the only problem. Okay, other observations? Okay. Now, let's go back to what I was saying in the beginning. Maybe you have an n-dimensional representation, and you want to find a sort of projection of your points so that you can reduce the number of dimensions that you use. So now, the next let's say subtopic of our course will be called, let's call it dimensionality reduction. Where you start with objects that are in an n-dimensional space, and you want to project them onto an n-dimensional space with n, lowercase n, small n, much smaller than big N. And possibly, if your final goal is to represent, to visually, to show your objects, n will be 2 or 3. But not always. Maybe you only want to reduce the dimensionality to make the system more affordable for your computer, for your algorithms. Okay. Well, to do this, consider this example. The problem is that okay, let's consider reduction from 2 dimensions to 1 dimension. You might remember some lessons ago when I was speaking about a recommendation system for movies, for example. We identified 2 possible dimensions that were the degree of, let's say, depth of the movie, maybe 0 or, let's go to -1. -1 means very easy to see, you don't need any mental effort. Here means you need a lot of culture, of will, and of intelligence to understand this movie. And the other dimension was, let's say, the seriousness of the topic. So it's just an evasion movie, and it's a movie about an important topic. Maybe if you want to get some amusement, then you should go on this side of the scale. Okay, so 2 independent dimensions. We all agree that movies may fall in all positions of this graph. Maybe, okay, we are straining between -1 and 1. So we have a square that represents some features of our movies, and every movie is a point in this space. But, okay, now, suppose that after looking at placing many movies in this diagram, you find a cloud like this. So, statistically, you would say that there is a correlation between the 2 dimensions. They are not independent of each other. Now, okay, now suppose that you want to represent these movies with only 1 coordinate. Which coordinate should you choose? Actually, by looking at this, they are more or less equivalent. Okay. You can either project the movies on the depth dimension or on the seriousness dimension, and more or less you get the same distribution of movies. So the idea is that, in a sense, depth and seriousness, if points are placed like this, if you choose depth, then seriousness does not add a lot of information to what you already know about the movie. If you know that the movie is deep, then you can assume with high probability that the movie is also serious. there might be some outliers, so some points that are not along this line, but if there are not so many, then you should concentrate with the main sequence here of points. Well, actually, if I had to choose a coordinate that best represents these movies, I would choose this coordinate. Why? Because, you see, it is that the coordinate that is best representing your movies is the one along which the movies have the largest spread. They are more spread out. In fact, if maybe I should have used a different color. If you use this reference frame, okay, so you rotate your reference frame like this, what you obtain is actually a system where one coordinate is much more representative than the other. Okay. So the idea is, let's find the coordinate transformation so that the first coordinate becomes the most important one. You see, in this case, if you take this reference frame, you can say that movies are represented by just one feature, one criterion, while the other one is a sort of error of small change that you apply to the points in order to have your movies. But the most important information is along this axis. Of course, what is the problem? That in this case, you could give names to your axis. This is a measure of depth, this is a measure of seriousness. It's difficult to give a name to this axis. This is actually some constant times depth plus some other constant times seriousness. Okay, well, this is the orthogonal one, so it will be some constant times, so the beta times depth minus alpha times seriousness. But rather than axis names, these are the formulas to obtain them. So, okay, so we can find a linear transformation so that one direction becomes more important than the other. But of course, we lose the original meaning of our axis. But we get to a system where it's easy to decide what dimension should be discarded in favor of the other. In a sense, we discover that in this movie data set, let's see, even though we chose two different criteria, what's really important to describe the movie is a linear combination of the two criteria corresponding to this axis. So what I would like to show you, but of course now we don't have the time, so probably I will do it next Monday, is, okay, let's introduce some rigorous formal statistical method to do this. And the idea is that, well, okay, let's say, even though you represent your objects in an n-dimensional space, actually not all n dimensions are important. But you can only discover that if you do some transformation of your data set before. Okay. In this case, okay, both dimensions look important when you look at each separately. You need to look at them together in order to discover that there is some direction that is more important than the other. And so we will see how to actually reduce the dimensionality, either to display our high-dimensional data set on screen, and to reduce the computational effort that we need to take in order to do something with our data set. This has applications on search engines, for example. You know, documents have TF, IDF representations that are maybe 10,000 dimensional vectors. You really would like to reduce that dimensionality because it would mean saving a lot of CPU per search. So we will see how this is done in statistical terms. But I'm afraid we will do it next Monday. Okay, tomorrow in the lab we will probably see something about the spring model, unless I find something more interesting to do, but we shall see tomorrow. Questions? Okay, that's it.